Good morning, everyone.
Morning, sir.
Good, good morning, sir.
Okay, so there is no disturbance, right? Are you able to hear me clearly?
Yes, sir. Yes, sir.
Yes, sir.
Okay, good. So I was just waiting for everyone to join. So that's why I'm starting at 5 past 11. So welcome back. And in yesterday's class, we understood the definition of fuel cells. How can we compare that with conventional energy system? And to recall the definition, so it's an electrochemical device which electrochemically converts chemical energy of reactants, fuel, and oxygen directly into electrical energy. When compared with conventional systems, the losses associated with energy conversion are comparatively
Excuse
less.
me, sir.
Yeah,
Sir, the PPT is not fully visible. Like we can only see half of the screen.
is it? Okay, just a minute. And now?
Yes, sir. Better, sir.
Okay, good. Okay, so and to continue further, it consists of electrodes, electrolyte, and an external load. So the setup is very similar to an electrolysis cell, and fuel is supplied at one electrode, that is anode, and usually it is hydrogen, and an oxidant is supplied at cathode, and usually it is oxygen. And because of the reactions that take place at the electrode electrolyte interface, so electrons move through the external circuit, which is nothing but the current, and the same thing is utilized by the load, and that's how electricity is generated in a fuel cell. And it is very important to make sure that the surface area that is available for the reaction to take place is maximum. So it is usually the interface where the electrode, electrolyte, and the fuel and oxidant come in contact with is the actual place where the reaction takes place. More such a surface area, better the reaction and higher the current that is generated. So for this purpose, there is a specific design that is required for a fuel cell. So in this very particular diagram, so it is this interface I'm talking about. So it is between the electrode and electrolyte. So looking at this diagram, on one end of the electrode, the fuel is supplied, that is hydrogen. On the other end of the electrode, on the other side of the electrode, electrolyte is available. So it is very much necessary for the fuel to find its way through the electrode and reach the electrode electrolyte interface on the other side. So for this purpose, the electrode is made as porous as possible. So it is the interface that is more important. It is the interface at which the reactions take place. So on one side there is electrolyte, on the other side of the electrode there is fuel. So the fuel should pass through the electrode and reach the electrode electrolyte interface for the reaction to take place. For this purpose, the design of the fuel cell and in particular electrode is very important, and electrode is made highly porous so that the electrochemically active surface area is high. And these are some of the reactions that take place. So when hydrogen is used as fuel and oxygen is used as oxidant, and the electrolyte is an acid. In such a case, so these are the reactions that take place. So at anode, the fuel hydrogen so gets oxidized, so it gets converted into protons and electrons. The protons move through the electrolyte and reach cathode, and the electrons move through the external circuit and reach cathode. So this is how it should happen. The electrons should not pass through the electrolyte, and the protons should not, or ions should not pass through the external circuit. And for these reactions to take place continuously, the fuel hydrogen and oxidant oxygen should be supplied continuously. So that is the requirement. And we also realized that the energy that can be generated from a fuel cell with respect to weight is more when compared with conventional energy generation systems, and we just went through few applications, and we learned the working principle as well. So with this we shall proceed further, and we did go through a few historical developments as well. And now, so let's try and compare the fuel cell with batteries. So when it comes to batteries, there are two types of batteries: primary batteries and secondary batteries. So what is a primary battery? So it can supply electricity as long as the reactants are available within the battery. It has a limited storage. Whatever chemicals that are stored in the battery will react and generate the electricity, and it ceases to work once the reactants that are stored inside the battery gets depleted. So that is a primary battery. So when it comes to a secondary battery, so it is possible to regenerate the chemicals that are present in the battery by charging it again. So there will be multiple charge cycles that a battery can be subjected to. After certain cycles, say around 500 cycles, for instance, so it will stop working. And also batteries are energy storage devices. So if we want to compare fuel cell with such a battery, fuel cell is energy conversion device. Okay, it is not a storage device, and energy generated as long as the fuel and oxidant are supplied. So that is how we differentiate between batteries and fuel cells. Okay, I hope you're able to listen to me, right? Okay, yeah. And so now, with whatever we have understood about fuel cells and its working principle, if we look at the current that can be generated from a fuel cell is two electrodes and electrolyte with whatever components we listed. That completely makes one fuel cell. So the electricity that can be generated from one such fuel cell is very little. In order to power the devices, or in order to draw more current from a fuel cell, so one fuel cell may not be enough. So for this purpose, we end up stacking fuel cells. We end up connecting multiple fuel cells. So that is what you're able to see in this picture. So here, three fuel cells are connected. So how does the connection go? Anode of one fuel cell is connected to cathode of another fuel cell. So on and so forth. Ultimately, the load is connected between the external fuel cells in the stack. So this is just the schematic representation. However, to practically stack fuel cells, so it may not be this simple. So in order to make these connections possible, we make use of a component known as bipolar plate. a bipolar plate sits between the anode and cathode of two fuel cells. So, and these bipolar plates have many functions. So one is it provides the structure and strength. It works like a framework for the fuel cell, and it acts as connection between anode of one fuel cell and cathode of another fuel cell, and it will also facilitate the flow of the gases. So usually when both fuel and oxidant are gases, and fuel is supplied at anode and oxidant is supplied on cathode. When a bipolar plate sits between anode of one fuel cell and cathode of another fuel cell, so it will be exposed to fuel on one side and oxidant on the other side. So the choice of material plays a role. Design of such a bipolar plate is important, and looking at the diagram on the left, see, you can make out the corrugations on one side of a bipolar plate. So these are the horizontal corrugations, and if you look at the bipolar plate on the other side, so you will see the vertical corrugations. So like this, a bipolar plate will have corrugations on both the sides, and it has multiple roles to play. Using such bipolar plates, the stacking of fuel cells is done. Okay, and coming to the structure of an electrode. So this is how porous it is. See, this is a scanning electron micrograph of an electrode. So all these blank spaces are the pores or voids, and these are the substrate particles. On top of the substrate, the actual catalyst particles, the black dots, are deposited. So usually electrode consists of a substrate such as carbon or graphite. On top of such a substrate material, the active catalyst material such as platinum is deposited. So the black dots on the surface of a substrate can be seen on the picture. And look at the magnitude, it is in the order of nanometers, and it will be highly porous. So a lot of pores can be seen, the void spaces in between. And this is how a typical electrolyte with a substrate material and a catalyst deposited on such a substrate looks like. And coming back to the bipolar plates, so this is how a bipolar plate looks like. So vertical corrugations on one side and horizontal corrugations on the other side, and such bipolar plates are placed between the fuel cells in order to make a stack. Okay, now coming to the other component, that is electrolyte. So of course there are different types of fuel cells, and in these fuel cells, in some cases the electrolyte is liquid, and in some cases the electrolyte is solid. So if we consider an example where an electrolyte is a solid material and which is a membrane, so this is how the fuel cell assembly looks like. So here in between the two electrodes, we have a solid electrolyte membrane. We have anode on one side and cathode on other side. And looking at the dimensions of these materials, so look at the size of the electrolyte and electrodes. So the electrodes are slightly smaller than that of the electrolyte, so that the flow of gases are facilitated, and also we can make it compact. And in order to avoid the leakage, so gaskets are used on either sides. So this is how the electrode electrolyte assembly looks like. So this is known as EEA or MEA, so membrane electrode assembly or electrode electrolyte assembly. So this is how it is, how compact it is. So and it can be as thin as just a few microns. So technology has advanced to such a stage that the commercially available polymer electrolyte membrane fuel cells will have the membrane electrode assembly in the order of just 40 to 50 microns. So that is how thin those assemblies are, and such assemblies are stacked together and covered by manifolds at the ends to make it a stack. And coming to stacking, uh, the another name that is used for stacking is module. Each module usually consists of 16 fuel cells. So 16 fuel cells are connected together, and it is called as a module. So 16 fuel cells are stacked together, and such a stack is known as module. And multiple such modules are used depending upon the application. Okay, and this is another variant of the design or fuel cell assembly. So where you see a different pattern of corrugations which facilitate the flow of gases. So here in on one picture on the left, you can see a stack of multiple fuel cells. So which is a polymer electrolyte membrane fuel cell in laboratory. So each of these fuel cells are monitored individually, and you can see that lot of other connections make the fuel cell system. So we are going to learn more about the components that are required other than the fuel cell stack itself in order to make the fuel cell system. So you can just see one such picture here on the left, which is under study in a laboratory. And on the right, so this is an example of a fuel cell system that is used to power an apartment. Okay, so for residential purpose, to suffice the power requirement of residents, a fuel cell stack or fuel cell system is used here. This is how a commercially available fuel cell looks like externally. Looks from external. Okay. Now, in the meantime, we have heard about different types of fuel cells. So let's look into little more details about that. When it comes to classifying the fuel cells, there are different criteria on which the fuel cells are classified. So one could be based on the operating temperature. The other could be based on the type of fuel that is used. The third could be based on the type of electrolyte that is used. And a few 5 or 6 fuel cells are listed here. So let's just try to learn more about these. Okay, so let's try to look at the fuel cells classification based on the type of electrolyte. So alkaline fuel cell, AFC, proton exchange membrane fuel cell, PEMFC, phosphoric acid fuel cell, PAFC, molten carbonate fuel cell, MCFC, solid oxide fuel cell, SOFC. So these are the 5 different types of fuel cells classified based on the type of electrolyte. Okay, so in the first case AFC, the electrolyte is liquid and alkaline solution. And the second one, the proton exchange membrane fuel cell, the electrolyte is a solid and it is a membrane. And phosphoric acid fuel cell, as the name itself indicates, the electrolyte is an acid here and liquid. So molten carbonate fuel cell. So here molten carbonates are used as electrolytes, and solid oxide fuel cell. So the electrolyte is a solid metal oxide. So we have one more fuel cell that is listed here, that is DMFC, that is direct methanol fuel cell. This is classified based on the type of fuel that is used. So here methanol is used as fuel instead of hydrogen. So that is why the name DMFC. So far we have learnt about the conventional H2O2 fuel cell, where fuel is hydrogen, and direct methanol fuel cell, where the fuel is methanol. So these two can be categorized under uh, type of fuel that is used. Okay, and the other five, AFC, PEMFC, PAFC, MCFC, and SOFC, can be categorized under type of electrolyte. And all these fuel cells can again be categorized based on the operating temperature. So looking at the operating temperature range that is listed here, so AFC operates in the range of 50 to 100 degrees centigrade, and this temperature range varies, means different temperature ranges are used at different places. So depending upon the book and depending upon the author, so different ranges are mentioned. However, this alkaline fuel cell is considered as low temperature fuel cell. Usually the operating temperature of such a fuel cell is between 50 to 100. However, there are exceptions where the AFCs are operated close to 200 degrees centigrade as well. So this is a wider range, but classification, it falls under low temperature fuel cell. So coming to PEMFC, again the temperature is in the range of, operating temperature is in the range of 30 to 100 degrees centigrade. This also falls under low temperature fuel cell. So the third one under that category is DMFC. Again, the temperature, operating temperature is close to room temperature, and it varies from 20 to 90 or 100 degrees centigrade. Next is phosphoric acid fuel cell. So here that operating temperature is around 200 degrees centigrade. So it is medium temperature fuel cell. And the other two, the molten carbonate fuel cell and the solid oxide fuel cell, so are okay. In case of molten carbonate fuel cell, the operating temperature is beyond 650 degrees centigrade. It is considered as high temperature fuel cell. And solid oxide fuel cell goes up to 1000 degrees centigrade, and it is categorized under very high temperature fuel cell. So low temperature, medium temperature, high, and very high temperature fuel cells. So this is how the fuel cells are categorized based on the operating temperature. So what are the different ways? One is based on the fuel that is used, another one is the type of electrolyte, third is the operating temperature. And application varies depending upon the operating temperature, and in some cases the capacity will also depend on the application. So this is about the classification. Now let's move on to the other components that are necessary to run a fuel cell. It is not just the stack of fuel cells that will do the job. There are many things before that and after that in order to make it an efficient electricity generation system. And these components will depend on the type of fuel and the application as well, and also the operating temperature. So, and these components other than the fuel cell stack are known as BOP, or balance of plant. So in this picture So this is the actual fuel cell module. So other than this, there are many other components which make the entire fuel cell system huge, and of course that depends on the application. So this is an example of a fuel cell system that is used for electricity generation, so grid power generation, which can be compared with the conventional electricity generation systems. So if you just consider a polymer electrode membrane fuel cell that is used in a car, you may not find these many components there, and it won't be as huge as this as well. Okay, so what are these other components that are necessary? Okay, so far when it comes to the usage of fuel, we just have come across two types of, we just have heard about two types of fuels. One is the hydrogen, other one is methanol. However, there are many other fuels that can be used in fuel cells. So even if we say that there are many other fuels, ultimately the component that is very important in the fuel is hydrogen, for most of the fuel cells. Of course, there are certain fuel cells which run completely without hydrogen, but in general, when we talk about fuel cells, the most common fuel is hydrogen, and uh, ideally it is pure hydrogen. However, there are other options where you start from other fuels and you generate hydrogen, and hydrogen is supplied along with other gases. So the main component of that mixture of gases will be hydrogen. So if we take such cases, uh, the natural gas, hydrocarbons can also be used as fuel for hydrogen. So in such a case, pre-processing of the fuel is necessary. Okay, so let's say we want to make use of the natural gas or any light hydrocarbons. So for that, I just would like to give you a little more background about the fuels. So the crude oil from which we generate the gasoline, diesel, gas oil, naphtha, so on and so forth, we generate such fuels from crude oil, and this crude oil is a fossil fuel, so which is obtained in earth crust, and it is available in different parts of the world. Depending upon the place from where it is extracted, the composition will vary. So some might have too much unwanted materials in it, and some might have too much of sulfur. So like that, the composition of the crude oil is depending on, or it depends on the location from where the crude oil is extracted. So depending upon the place from where it is extracted, the processing steps will also vary. Okay, ultimately the requirement of fuel, irrespective of from where the crude oil comes from a vehicle viewpoint, is always the same. However, the steps involved to get the required fuel from a crude oil completely depends on from where the crude oil is obtained. And what are these steps that are usually followed in refineries? So what happens? Crude oil comes to refineries. In refineries, they break down those that crude oil into multiple components, and some of the processes that are used are desulfurization, hydrodealkylation. So these are the two common steps that every refinery will involve. So what happens here? Uh, the crude might have lot of sulfur content. Sulfur is always an issue when it comes to fuel. So invariably the sulfur should be removed, or the allowable content of sulfur in fuel is very crucial and critical. So if you consider the norms set by the government, such as Bharat Stage 4, Stage 6, or Euro 4, 5, or 6, so they every time they specify the allowable content of sulfur in fuel. So with that, at present, the allowable sulfur content in any fuel that can be used in automobile is just 10 parts per million. So it should be less than 10 ppm. So it is very stringent with respect to the sulfur that can be present. And there are many reasons for this. So one is, so the pollution will be high. So oxides of sulfur generated will be high when more sulfur is present. On top of that, so knocking of engine takes place. So sulfur damages the components of the engine when it is present in the fuel. So these are two main reasons why sulfur should be restricted to a certain percentage in the fuel. So why am I speaking all these? So I just want to convey one of the methods that are involved in processing the crude oil before we get the required fuel. So like that, depending upon the type of fuel that is used, a desulfurization unit may be necessary in a fuel cell system in order to get the required hydrogen, which can be supplied to fuel cells as fuel. So for that, in this picture, we see a desulfurization unit, and hydro dealkylation is another process where you will end up converting unsaturated hydrocarbons into saturated hydrocarbons by making use of hydrogen. You will treat the fuel with hydrogen and convert that into saturated hydrocarbons. So more the saturated hydrocarbons, better the performance of the fuel. And so for that purpose, you might have a hydrodealkylation unit, or another way of producing hydrogen from hydrocarbons is so steam reforming. So for that purpose, you may see a reformer. So these are some of the components that are necessary to make the entire fuel cell system. And there will be a lot of heat exchangers and steam generation units, blowers, control systems, so converters. So these are some of the components that are required other than the fuel cell stack to make the fuel cell system. Okay. So now we are talking so much about this fuel cells, and it is used for electricity generation. And for this purpose, we need certain terms in order to compare the performance of fuel cells with other conventional energy generation systems. And these terminologies should be common everywhere. So whoever speaks about fuel cell should use these terminologies only, so that everyone understands what they're speaking. For that purpose, certain terms are used, defined. It could be to compare among the fuel cells as well, and to compare a fuel cell system with other conventional energy generation systems as well. So one such parameter is current density. So here it is current per unit area. So what is this unit area we are talking about? We realized that the effective electrochemically active surface area is very important, or the amount of current or electricity that is generated from a fuel cell is directly proportional to the active surface area that is available. So what is this active surface area? It is the interface between the electrode and the electrolyte. So more the active surface area, better the performance of a fuel cell. So taking that into account, keeping that in mind, so the current that is generated from a fuel cell is always expressed per unit area of an electrode. So that is what we are talking about here. So it is the current density, which is nothing but current per unit area. So if nothing is mentioned, it is always understood that the unit area is the area of the electrode. In some cases, they speak about the unit area of the electrolyte as well, when it is a membrane or a solid electrolyte. Until and unless they specify whether it is electrode or electrolyte, it is always assumed as the electrode. That means if they just say current density, it is always the current per unit area of the electrode. And this is also used for comparing fuel cell electrodes and electrolytes. And the units are milliamperes per centimeter square or ampere per feet square. So current density, which means current per unit area, and what are the units? Milliamperes per centimeter square or ampere per feet square. And whenever we talk about current density, there is an associated voltage. So it is very important to specify the voltage at which the fuel cell is operating while talking about the current density. And usually that is about zero point 0.6 to zero point 0.7 volts. And this may vary depending upon the type of fuel cell. So far we have learnt one term, that is current density. And another such term is power per unit area. So you have to make out the difference here. So even though the reference is same, that means we are talking about unit area in both the cases. When it comes to power, so power density is not power per unit area. Okay, or power per unit area is not expressed as current density. But when it comes to current, so current density is current per unit area. But when it comes to power, so the power per unit area is not expressed as power density. So you have to pay attention to this. And so here, how do we calculate or get the power per unit area? It is product of current density and voltage, and it is usually expressed as milliwatts per centimeter square. Okay, so there it is milliampere per centimeter square, here it is milliwatt per centimeter square, but there it is current density, but here it is simply power per unit area. That is the second term that is used in common. Okay, and okay, the third term is power density. So power density is power per unit volume. Current density is current per unit area. So along with these two, there is one more term, power per unit area. So I am purposefully repeating this multiple times so that you will keep this in your mind and you will be able to differentiate better. Okay, and fourth term is specific power, and this is power per unit mass. So when it comes to power, there are three variants. One is with respect to mass, another one is with respect to area, third is with respect to volume. But when it comes to current, it is only with respect to area, and it is known as current density. Okay. So units of specific power, watt per kg, power density, milliwatt per meter cube. Okay, and when it comes to the cost of a fuel cell, it is usually the fuel cell system which will be quoted, and the normal convention is the US dollars per kilowatt. So how much does it cost in US dollars per kilowatt of power that is generated? Okay, and life cycle of a fuel cell is represented in percentage deterioration per hour. How much deterioration will take place per hour? Or another way is they just express how many hours a fuel cell can work. Okay, so one usual representation is milliwatt per 1000 hours. With this, if we look at the price of the fuel cell systems, one is a normal system, that means which can be used for domestic or household purpose. In such a case, so one term is the with respect to power kilowatt, how much does it cost? So it is $10 per kilowatt. And how much volume does it consume per kilowatt? That is kilowatt per liter. And for how many hours you can run that fuel cell. So 4000 hours. And it is assumed that if you operate it 1 hour per day, so you can use it for over 10 years. And there is another system known as combined heat and power system, so known as CHP. So here, along with the electricity that is generated from a fuel cell, there is lot of heat that is generated because of the functioning of the fuel cell, which is known as waste heat. That heat is recovered and steam is generated from that heat, and again you use that steam to generate further electricity. So that is known as CHP, combined heat and power, where you generate additional electricity by making use of the waste heat that is generated from a fuel cell. So such systems are known as CHP systems, and it is expressed. There is a way in which you express the price or cost of such systems as well. So the price will be slightly higher. It will be in the order of $1,000 per kilowatt. And again, volume is considered kilowatt per liter. And even the working hours of our life cycle of such a fuel cell is also high. So it is usually around 40,000 hours. So these are some of the terms that are commonly used to compare fuel cells and also to compare fuel cells with other conventional energy generation systems. So for today, I just would like to stop here and we shall continue the rest in the next class. And again, I would like to take attendance today. Give me a minute for that. So,
Excuse me, sir.
yeah,
Sir, can you tell us more about the experiential learning, sir? Like,
say again.
like what all we have to do for the project?
Okay, you mean for the self-study or experiential learning?
Yes.
Okay, so who is this? This is Pavan. Uh, what I suggest to you is you just finalize the groups. I'll give you more detailed explanation about how it is going to be carried out, and also you should specify whether you would like to work on review paper or on development of a prototype. So depending upon that, what exactly you have to do, I'll explain. Is that okay?
Okay, sir.
Yeah. So I think the deadline is to finalize
20th.
the teams is 20th, right? Yeah. So kindly do that. After that, once the team is frozen, so I will explain both the cases. In case if you want to do the review paper, what exactly you're expected to do, and also in case of the prototype development.
Okay, sir.
Yeah. Okay. So just a minute. Okay, today is 16. Pradeep Kumar from Aerospace.
Present, sir.
Okay. And Nandini, Nandini K.
Yes, sir. Present, sir.
Okay. Aditya Datta from Aerospace. Sharat, MG Sharat.
Present, sir.
Okay. Prajwal Hiremat.
Present, sir.
Shritij.
Present, sir.
Ravi Krishna.
Yes, sir. Present, sir.
Okay. Pavan from Biotech.
Present, sir.
Nisha. Nisha V.
Present, sir. Present.
Okay. Spurti BV.
Present, sir.
Okay. Riya Sharma.
Present, sir.
Abib Sarath is attending a workshop. Okay. Soumya.
Present, sir.
Okay. And Shreya NM.
Present, sir.
Apurva K.
Present, sir.
Okay. Amulya Rao. Workshop. And Prasanna Reddy.
Yes, sir.
Harini Subramanian.
Present, sir.
Okay. Preksha Shetty.
Yes, sir.
Ambrish. Srinidhi Rachappa. Praveen Khanna.
Present, sir.
Okay. Aditya Anand. Pooja Pooja from Computer Science.
Aditya Anand present, sir.
Aditya is present. Okay. Prerna KS.
Present, sir. Present, sir.
Okay. Divyanshu Anand.
Present, sir.
Okay. Geeta Shivani.
Present, sir.
Rishika Rai.
Present, sir.
Okay. Himanshu.
Present, sir. Master Present, sir.
Okay. Yeah. Anirudh Devpura.
Present, sir.
Okay. Ayush Srivastava from Computer Science. And Sandesh Nayak from Civil. There are few questions. I will answer those questions in a minute. Okay, Sandesh is present. Okay. And Mahant.
Present, sir.
Okay. Rajashekar.
Present, sir.
Utkarsh Kumar.
Present, sir.
Ajay B.
Present, sir.
Mahesh Basavaraj.
Present, sir.
Okay. I suggest you guys to keep your microphone on mute when you are not using it. Shahid.
Yes, sir.
Keep it on mute. Mute your microphone, please. Yeah, thank you. Santosh.
Yes, sir. Present, sir.
Santosh Dodamani. Okay.
Present, sir.
Srinath L from Civil. Mithun K.
Present, sir.
Okay. Satyansh Singh.
Present, sir.
Okay. Saurabh.
Present, sir.
Kittur.
Present, sir.
Okay. Sharan C.
Present, sir.
Tushar Goyal.
Present, sir.
Subhash VN.
Present, sir.
Channabasava.
Present, sir.
Gundappa. Kiran K.
Sir, present, sir.
Salim.
Present, sir.
Okay. Rohan Akash.
Present, sir.
Saim Agarwal from Civil. Nitya R.
Present, sir.
Okay. Arpit Kapil.
Present, sir.
Suman Saurabh.
Yes, sir. Present, sir.
Okay. Sheetal SP. Yashika.
Present, sir. Present, sir.
Okay. Shahid. Shahid Bashir Malik.
Yes, sir.
Okay. Kushal. Kushal R.
Present, sir.
Okay. John Bosco from electronics. Anuraj Jha from electronics. Ujjwal Mahendru.
Present, sir.
Okay. Arijit Banerjee. Shubham Bansal.
Present, sir.
Okay. Kushagra Kumar.
Present, sir.
Fatima Tabassum. Ishita Mudaliar.
Present, sir.
Zainab.
Present, sir.
Okay. Anirudh Sharma.
Present, sir.
Akash Tripathi.
Present, sir.
Nalin Kamal.
Present, sir. Present, sir.
Okay. Jayat.
Present, sir.
Okay. Girish Gowda. Pranav Pathak.
Present, sir.
Okay. Prajwal Panchangam.
Yes, sir.
Ketan. Yes, Ketan. Darshan. Yes, Darshan.
Yes, sir. Yes, sir.
Okay. And Mahadev. Mahadev R.
Present, sir.
Okay. Kushal Gowda. Himanshu Sharma.
Yes, sir.
Ronak R.
Present, sir.
Okay. Sagar Beswari.
Present, sir.
Tushar
Present, sir.
Agarwal. Okay.
Present, sir.
Purvi from Information Science.
Present, sir.
Aditi Dora.
Present, sir.
Riza.
Present, sir.
Okay. Abhirup. Abhirup Saha.
Present, sir.
Ashutosh Agarwal. Aditya BS.
Yes, sir. Present, sir.
Okay. Rakshit. Rakshit Kamath.
Present,
Rakshit.
present, sir.
Okay. Rishabh Bhargava. Srinath is present. Okay. Rishabh Bhargava and Bhavit Shetty. Anuj Kumar Nigam.
Present, sir.
Okay. And Ashwin Sudarshan. Sadashiva Hebbal.
Present, sir.
Okay. Mallika Gowda. Sohangi Srivastava. Nabira Shivansh.
Present, sir.
Ayush Srivastava from Electronics.
Present, sir.
Okay, but Ayush, I haven't received the letter yet from Dean with your name included in it.
Actually, Sam Siddharth speaking, sir, from Civil. Like, even
Yes,
like
Yes, Siddharth, I am taking your attendance today, but I still haven't received the updated list from Dean in which your names are included. So kindly follow up and ask Dean to, or you collect it from Dean and send it to me.
Okay, okay, sir. Okay, sir.
Yeah,
Yes,
not for your department, but for the course fuel cell technology.
yes, yes.
Okay, fine. Yeah, thank you. Is there anyone else? Did I miss?
Excuse me, sir. Fatima Tabassum from EI
Is
department.
present. Okay, Fatima
Sir,
is
Aditya
Yes, sir.
present.
Datta Aerospace.
Just a minute. Fatima is present. And
Aditya Datta.
Aditya from aerospace. Aditya, just a minute. Aditya, okay.
Thank you so
And
much, sir.
yeah, Ashwin Sudarshan. Ashwin Sudarshan from which department? Okay, anyways, I'll make note of that. Okay, and a few general Mahesh Basaraj from civil. Mahesh Basaraj from civil. Yes, I have marked it present. Okay, and I hope you are able to listen to me for the entire duration. If there is interruption in between, kindly bring it to my notice. And if you have any questions, feel free to interrupt and get all your doubts clarified. So this is a theory course, so it will be comparatively little dry. So feel free to interrupt me and get all your doubts clarified. I hope whatever we have discussed from the past 2 days, you are able to make out and understand. Yeah, with respect to the self-study, Ashwin, from which department are you? Ashwin Sudarshan.
Sir, he's from mechanical, sir.
He's from
Ashwin is from
mechanical.
mechanical.
Okay, so I'll mark his attendance. Ashwin Sudarshan. Okay. Yeah, with respect to the number of students in a group, so I restrict that to 3 or 4, so not less than 3 and not more than 4. And remember, you have to make use of the entire duration very well in order to come up with a good review paper that is acceptable in any Scopus indexed journals. So you have to come up with at least 200 papers. So that is collectively, if it is a group of 4, it is 50 papers per person. So on an average, if you are able to find 5 or 10 per week, so it's decent enough. So make sure that you work on it regularly. It is not something that you can complete on by spending just 1 or 2 days at the end. So you have to work regularly every week on it, and more information will be provided once you confirm whether you would like to work on review paper or a prototype. So prototype development will be challenging, but at the same time very rewarding. So who is really interested to learn more about fuel cells, I am sure that you will definitely learn more than what you get to hear in the class, and it is going to be very interesting as well. So you are free to choose one out of the 2. Okay, so thanks very much for your attention. We shall continue the discussion on Friday. So remember, you have to give names before 20th. Any questions? Okay, if not, thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Okay.
Thank you.
Okay.
Sir?
Yeah? Who's that?
Sir? Sir, I'm Praveen, sir.
Yes, Praveen.
Sir, topics can be finalized after 20th also, no, sir?
Topics. Yes, topics can be finalized. I suggest you come up with a tentative topic by 20th itself, because for that itself we take too much of time, so we may not be able to make use of the available duration effectively. So what I suggest you is you
Okay.
come up with a topic within 20th. And
Okay, sir, fine.
you are from biotech, right?
Yes, sir. I am from Biotech.
Yeah, I have given a few topics. I have suggested few papers on group, so that is just indicative. So what I suggest you is, if you can say, for example, if you want to work on microbial fuel cells, in that case you think of integrating the computational strength. Okay, so you try to bring in
Yes.
the computational functionality and try to find out or simulate or model how the growth of microbes or columns, microbial colonies grow and multiply. So now what is their life cycle, so on and so
Yes.
forth. That is just one example. Like that, you feel free to choose a topic
Yes.
uh, where you can add value to whatever that is already existing, because a whole lot of work, a lot of ample amount of work is carried out when it comes to
Yes, sir.
microbial fuel cells. It is completely matured. There are no gaps at all. In spite of that, if you want to do something really good and if you want to come up with a review paper, so we should find out new avenues, such as adding computational components to the MFCs. So think in those lines.
Yes, sir.
Yeah.
Okay, sir, fine.
Okay. Yeah. Thank you.
Thank you, sir.